Hello guys, in this part of video, I'll be showing you how to find center of mass by integration method. Okay, so first of all, I would like to explain what are the terminologies regarding center of mass by integration methods. Here, in integration methods, we will be using some terminologies like lambda, okay, sigma, rho, this kind of mass densities we will be using. So what are these terminologies? Let's see now. Lambda means what? Lambda is called linear mass density. Okay, linear mass density. It will be linear mass density. Right? Means whenever we will be having some kinds of object like linear shape, okay, like a rod, okay, like we have this kind of rod as here, rod. So what I'll do, I will try to resolve this rod in small differential elements. So, okay, so I'll take an element at a distance of x from any of the end, and this is my dx. So its mass will be called as dm mass. So since it's a linear kind of object, so its mass density will be called as linear mass density, and that will be nothing, it will be mass per unit length. Okay, mass per unit length. So its unit will be kg per meter. Its unit will be kg per meter. So in this kind of shape, wherever you will finding linear objects, in that case we will be using linear mass densities, and in that case we can write our dm as lambda times of dx. Okay, from unitary method, because unit mass length is lambda, so dx mass length will be lambda times of dx, right? Next will be our surface mass density, which will be called as sigma. Sigma is called surface mass density. Surface mass density. Surface mass density, and its unit will be obviously kg per meter square. So mass per unit area. So unit will be kg per meter square, right? So whenever we have some objects like disc, okay, square plate, that kind of shape will have linear mass density, because those kind of shape will be having linear mass density because the entire mass will be distributed among the area of the entire shape. Okay, suppose this is my disc. Okay, now we can see this triangular plate also here. Okay, so what is the area of the disc? Suppose it's a rectangular disc having length L and width as b, and the entire mass of the system is capital M. So the sigma will be written as M upon L into B, right? Here suppose H is the height of the triangle and base is B. So here sigma will be written as, sigma will be equals to mass per unit area, half into base times of height. So sigma will be equals to 2m upon bh. 2m upon bh. So whenever we will be having these kinds of objects, like it will be laminar object, in that case the surface mass density term will be used. Okay, so we will take an element here and we will be writing dm mass. So dm mass will be nothing, it will be sigma into small area of the elemental part of the body. Okay, suppose we have taken here dA area here, strip. We can resolve this into small strip. So its area will be dA. So in that case, dm mass we can write sigma into dA, right? Here also we can resolve this. And the last one is volume mass density. This is represented by rho. It's called as volume density or volume mass density. Volume mass density. Okay, and it is written by mass per unit volume. Mass per unit volume. Okay, so its unit will be kg per meter cube. Its unit will be kg per meter cube. So whenever like we have spheres, okay, solid sphere we have, suppose solid sphere. Okay, So in that case, volume mass density, we will be using volume mass density because the mass will be present in the entire volume of the system or sphere. So in that case, we'll write mass per unit volume, which is volume of the sphere will be 4 by 3 pi r cube. Okay, so this is the mass density of the sphere having radius capital R. So these are the three terminologies which will be used in order to find out the center of mass by integration methods, right? So by integration method, we have three formulas by which we can find the center of mass of the extended objects. Okay, so center of mass of x coordinate of center of mass can be written as 1 by m into integration of x dm, right? What is x here? X is the x coordinate of center of mass, coordinate of center of mass of dm mass, right? X coordinate of center of mass of dm mass. Similarly, ycm is 1 upon m into integration of ydm, and where y is what? Y is y coordinate of center of mass of dm mass. Y is y coordinate of center of mass of dm mass, right? Similarly, ZCM is written as 1 by m upon integration of ZDM, and Z is again Z coordinate of center of mass of dm mass. So here you can see this, that in this formula there is another term is here which is dm. So according to given situation, you have to take the dm mass. What is dm here? It is the infinitesimal or in differential mass, infinitesimal mass of the body. Let us understand this one. Means the smallest mass in which we can break that entire shape or the body. Suppose we have this ring, semicircular ring, right? So how we can resolve the semicircular ring? We can resolve the semicircular ring in very small element. So small element, we can take the d theta element here, and we can resolve this. We can think that it is made of very small element, and its length will be r d theta, as r is the radius of the ring. In the same way, we can resolve triangular lamina. Triangular lamina can be think that it is made of very small rectangular strips. Suppose the strip will have thickness dy, okay, and its length is, let's say, x or 2x, okay. So the area of the strip will be 2x into dy. So here we will be using sigma, and we will be writing dm mass as sigma times of area of the strip. So in this way, we can see that different shape will be having different types of dm mass element. It depends upon the shape of the object. Here the ring was resolved in this way. Here the triangular lamina is resolved in strip, okay, and hemispherical shell, okay, and solid hemisphere we can resolve in another way. So let's see, first of the example is how to find center of mass of semicircular ring, okay. So semicircular ring, how we can find the center of mass of semicircular ring, we will see here. So what I'll do, I will take an elemental mass which is forming d theta angle at the center of the circle, and it is forming at an angle theta from the horizontal. So this angle is my d theta, okay. So this angle is my d theta. So the length of the elemental mass will be r d theta, Okay, so the length of the elemental mass will be r d theta. First of all, we will define here mass density, which is linear mass density, and that will be written as m upon pi r, right? So what is dm mass here? Dm mass will be written as lambda times of dl, that is my dl length here, and dl will be nothing, it will be r d theta. So lambda into r d theta. What is lambda here? Lambda is m upon pi r into r d theta. So r is getting cancelled out, and from here we are getting dm equals to m upon pi into d theta. So we got dm. Okay, so now our method is by integration method. As you can see, this figure has symmetry along y-axis. Okay, so entire mass is present along the y-axis. So this figure or the semicircular ring will be having center of mass along the y-axis only. So x coordinate of center of mass of this ring will be 0. So this figure can be replaced like this. If you see, we can replace this figure. Okay, because see here, if you want to find the coordinate of this particle, so this will be r cos theta and this will be r sin theta. Okay, this is r sin theta, this is r cos theta, this is r sin theta. Okay, r cos theta and r sin theta. So we can see this figure like this. We have a dm mass here, and dm mass coordinate is r cos theta comma r sin theta, right? So its xcm is 0 as due to symmetry, and ycm is 1 by m into integration of y dm. What is y here? Y coordinate of center of mass of dm mass. What is y coordinate here? R sin theta. So I'll be writing here 1 by m into integration of r sin theta into dm. And what is dm here? dm is m upon pi d theta. dm is m upon pi into d theta, right? M is getting cancelled out here, and we can take our r by pi as common. So integration of sine theta d theta. Okay, so now what is the integration limit from here? Limit of integration must be from 0 to pi. Why? Because the entire limit is present into 0 to pi region. So the integration limit will be here from 0 to pi. And the integration of sine theta will be minus cos theta. So from here what we can write? R upon pi minus cos theta 0 to pi. And it will be r upon pi minus cos pi will be 1 and cos 0. So it will be 2 here. 1 plus 1 will be 2. So the center of mass, y coordinate of center of mass will be coming as 2r upon pi. So in this way we can see that. So next we will be seeing how to find center of mass of semicircular disc. Okay. So in this problem or derivation, what I'll take, I have to take the elemental mass dm. Okay, so we can think that this entire semicircular disc is made up of semicircular rings. Okay, we can break the elements of the semicircular disc into rings. Okay, so the ring will be my elemental mass. So I have taken a ring of radius small r, okay, from the center. The radius of the entire semicircular disc is capital R, and the radius of the ring, this ring, okay, this ring, radius of this ring is small r, and the thickness is dr, right? Thickness is dr. So now first of all I will write sigma here, because the mass density will be sigma here. So what is mass density? Mass per area. Area of the disk will be pi r square upon 2. So pi r square upon 2 will be the area of the semicircular disk. So we got sigma. Now I will write dm. dm is the small elemental mass of this ring. So that will be sigma into area of that small semicircular ring, right? So what is dA here? dA will be area of that semicircular ring. If you unfold this ring now, what will happen? This ring will be having length as how much? Pi r, because it is semicircular, and the width of the ring will be dr, right? So what will be the area of this rectangle? If you unfold this ring will have length pi r and the thickness will be dr. So dA will be pi r into dr. So dm will be sigma into dA. Sigma is 2m upon pi r square into dA is pi r into dr, right? So if you cancel out this pi from here, so you will get dm value as 2m upon r square into small r square into dr, right? So now from symmetry what we can say, x coordinate of center of mass of the disk will be 0. Why? Because there are no elements present along the x-axis. The entire elements are present along the vertical y-axis. So x coordinate of center of mass of this disk will be 0. Now what is the y coordinate of center of mass? Y coordinate of center of mass formula we will be using here. Y coordinate of center of mass YCM is 1 by m integration of ydm, right? So what is y here? Y is the y coordinate of center of mass of dm mass. As in my previous video, you have seen that center of mass of semicircular ring is 2r by pi. So y is the y coordinate of center of mass of dm mass. dm is my elemental ring. So its center of mass will be at a distance of 2 small r by pi. So I'll substitute the value of y here and dm also. So y will be, small y will be 2r upon pi into, if you put the value of dm here, it will be 2m upon r square into small r square dr. Okay. So, and small r is varying from 0 to capital R. m is getting cancelled out. You can take 4 upon pi r square as common and integration of r cube dr from 0 to r. How much it will be coming as? Integration of small r cube dr will be nothing, it will be r to the power 4 upon 4. Okay. My mistake here, I've written by mistake r square dr, that will be r dr here. Okay, not r square dr, it is r dr. So it will be r dr, right? R dr here. R dr. So here you will be getting as r square dr. Okay, so integration of r square dr will be r cube by 3, and after solving this, 4 by pi r square into r cube upon 3, so it will be coming as YCM is coming out to be 4r upon 3 pi. 4r upon 3 pi. So center of mass of semicircular disc is come out to be 4r upon 3 pi. Here the calculation mistake was there because it was coming r dr, but by mistake I have written as r square dr. Keep in mind this one. Okay. So r dr it will be, right? So the answer will be YCM equal to 4r upon 3 pi. Now next we will see how we can find the center of mass of hemispherical. So guys, next we will be watching for center of mass of hemispherical shell. Okay. So how to find center of mass of hemispherical shell? That is my next topic. Okay. So here, what I'll do here, same process I will repeat here. I will take my dm mass, elemental mass. I will go from origin here, okay, at an angle theta, and I will take d theta element here. Okay, this is my, so I will resolve this entire hemispherical shell into small elemental circular rings. Okay, so this is my circular ring, and this circular ring having width as r d theta. Okay, so this circular ring will have width as r d theta, and its radius will be how much? Its radius will be this one. Okay, this is the radius, which is nothing, it is r cos theta, and its center of mass, this one will be at a distance of r sine theta from the origin. Okay, so this is r cos theta is the radius and r sine theta is the center of mass from the origin. So what we can write here? So first of all, what is my sigma here? Sigma will be mass upon surface area of the hemispherical shell, which is 2 pi r square. And what is dm mass here? Dm will be sigma into area of that ring. So area of that ring will be 2 pi r cos theta into r d theta, 2 pi r into dr. So 2 pi r, r means radius, radius is r cos theta. Okay, radius of the ring is r cos theta into width, width is r d theta. So this is my dm mass. We got dm mass as sigma into 2 pi r. Here pi is missing here. It will be 2 pi r, 2 pi r cos theta into r d theta, right? So we can simplify this. So we can write dm equals to sigma is 2 pi r square into 2 pi r square cos theta d theta, and 2 pi r square will get cancelled out, and from here you will be getting as dm equals to m cos theta d theta, right? So we got dm as m cos theta d theta. Now our next process will be we have to find center of mass. Y coordinate of center of mass we have to find, because due to symmetry the center of mass will be lying along the y-axis only, because it has a symmetry along the y-axis. So y coordinate of center of mass will be 1 by m into integration of y dm. Y dm means y is the y coordinate of center of mass of dm mass. So where is the center of mass of the ring is? It is at a distance of r sine theta from the origin. So I'll be writing here r sine theta as my y value into dm. Dm is my this much. Dm is m cos theta d theta. So I'll be writing here m cos theta into d theta. So m is getting cancelled out, and from here I'll be getting as ycm equals to, I can take r outside as common, and in the bracket it will be sine theta into cos theta. If you multiply and divide it by 2, so it will be 2, here it will be sine 2 theta d theta, and the limit will be from 0 to pi by 2, right? From 0 to pi by 2, the limit will be from 0 to pi by 2, because if you integrate from 0 to pi by 2, so the automatically left part of the figure will be covered, right? So the integration of this I will show in the next slide. Integration of this one is ycm. What I have written there? Ycm equals to 1 by ycm. It was r by 2 integration of sine 2 theta d theta 0 to pi by 2, right? So r by 2 if we take outside common, and integration of sine theta will be minus cos 2 theta upon 2, 0 to pi by 2, right? Now I will put limits here. If I put limits here, What I'll write here? So it is YCM equals to R by 2. Limit, you can take 2 as common denominator. So minus cos 2 theta. Theta will be pi by 2 and plus cos 0. Okay. So cos pi is minus 1. So minus 1 will be plus 1. 1 plus 1, 2. So 2 will get cancelled out. It will be coming as R by 2, 2 by 2. So answer will be YCM equals to R by 2. So for hemispherical shell, the center of mass will be lying. For hemispherical shell, the center of mass will be lying at a distance R by 2 from its base. Okay, here it will be lying. Now I will take next. So next topic I'll be taking as center of mass of solid hemisphere. Okay. So for that we have to take our dm mass element. Okay. So we can resolve this entire hemisphere, solid hemisphere. We can think that it is made up of small discs, or we can resolve it in small hollow hemispherical shell. It is upon you that in which way you want to resolve this. Okay, so I am going to resolve this. I am going to take the elemental mass as my disk. Okay, so I can resolve this into small discs. So I'll be taking a disk. I'll be taking a disk which is at a distance which is at a distance, let's say this is at a distance of small x or y. This is at a distance of y. Okay, at a distance of y. Its center of mass of the disk is at a distance y from the center and having thickness as dy. Okay, so this is my elemental disk. So first of all, I would like to write its mass density. Here it's, since it is solid hemisphere, so its mass density will be rho equals to mass upon volume. So volume will be 2 by 3 pi r cube. So basically it will come out to be 3m upon 2 pi r cube. Now what is dm mass? Dm mass is the mass of this elemental disk, right? So dm mass will be rho into volume of that disk. What will be the volume of this disk? Volume will be area into thickness. So area will be pi, okay, pi into radius. What is the radius of this disk? If you see this, the radius of the disk will be this is the radius, small r. Okay, so small r, this is the small r. So small r can be written in the form of y and capital R. So small r will be it's a, if you take this small r, this is capital R, this is y. So what we can write small r as, this will be root over of r square minus y square. It will be root over of r square minus y square. So dm will be, area of the disk will be pi small r square. If you do pi small r square, that will be pi r square y square into thickness is dy. So this is the volume. Okay, so this is my dm mass. If you substitute this value here, it will be coming out to be 3m by 2 pi r cube into pi r square minus y square into dy. Right. So this is the dm mass we got here. Now what we will do here, we have to find the center of mass of the solid m into integration of y dm. So dm mass, if you put the value of dm mass there, y into dm mass was 3 by 2 pi r cube into m, okay, into pi r square minus y square into dy. Right. So pi is getting cancelled out, m is getting cancelled out. and from here YCM is coming out to be, we can take 3 by 2 r cube outside. So inside in the bracket you will write, okay, and r is y is varying from 0 to r, so the limit of y will be from 0 to r. So by solving this by integration method, what I can write here, r square, and this will be y dy integration 0 to r minus integration of this will be, means first of all I'll write this, it is y cube into dy integration 0 to r, right? So from here we can solve this, and I'll be getting as YCM equals to 3 by 2 r cube, okay, in the bracket its integration will be r square by 2, so finally it will be r to the power 4 by 2, and minus this will be r to the power 4 by 4. So its solution, this will be r to the power 4 by 2. Okay, so finally YCM will be coming as 3r upon 8, 3r upon 8, right? So center of mass of solid hemisphere will be lying at a distance of 3r by 8 from its base. Okay, so it will be here 3r by 8 from its base, center of mass, right? 3r by 8 from its base, right? Okay, so next I'll be going to explain about center of mass of triangular lamina. Okay, center of mass of triangular lamina, triangular lamina. How to find center of mass of triangular lamina, right? So triangular lamina, here it is like this, and from base and from top, our wish from where we can find it is it depends upon us from where we have to find the center of mass. Okay, so what I'll do here, I'll be taking some element, dm mass element. What I'll do, the height of the triangular lamina is, let's say, h, and base is, let's say, 2b. Okay, base is 2b. So what I'll do, I will resolve the element of the triangular lamina into small strips. We can think that it is made up of small rectangular strips. Okay, so I'll be taking down so the width of this strip is dy, and from the apex this distance is y. Let's say this is my x. Okay, so the entire length will be 2x. So what is the first of all, what is the surface mass density here? Sigma will be mass upon area of the triangle, which is half into base into height, so finally it will be coming as m by bh, m upon bh, right? M upon bh we got. Now what is the area of that strip? The strip area, that we will write dA. Okay, what is the area of the strip? dA will be length into width of the strip. What is the length of the strip? 2x into dy. 2x into dy. Be careful, don't take x, because the length of the strip is 2x into dy. Now again there is some difficulty here. What kind of difficulty, sir? Because here are two variables are working here, x and y both. Okay, x is also varying from 0 to b, and y is varying from 0 to h. So we have to bring this variable into one of the form. Okay, so how we can bring this format into one single format? By similarity of triangle. We can see that there are two triangles, this triangle and this triangle. Okay, so these two triangles are similar. Which one? This one and the entire big one. These two triangles are similar. So what we can write from here? We can take the ratio of the sides in the proportion. Okay, So y upon h, from the triangular similarity, what we can write? Y upon capital H equals to x upon b. X upon b, this is b. So from here what we can write? X equal to by upon h. So we got x equals to by upon h. We can substitute it here. Now what is dm here? Dm will be sigma into dA. Sigma is my m upon bh into dA. dA will be 2x into dy, and x is my by upon h into dy. Right? So b is getting cancelled out here. B is getting cancelled out here. And what we can write here? That dm came out to be 2m upon h square into y dy. We got dm as 2m upon h square into y dy. Right? So now again we have to find the center of mass by putting these values in y dm formula. Because ycm will be integration of y dm 1 by m. Right? Integration of y dm 1 upon m. So 1 upon m, y is y, and dm is, you can see from here, dm is my 2m by h square y dy. 2m by h square y dy. 2m by h square into y dy. M is getting cancelled out. We can take 2 upon h square outside. So integration of y square dy. Y square dy. Y is varying from 0 to capital H. Small h, sorry. 0 to small h. Right? Y is varying from 0 to small h. So from here what we can write? Ycm is coming out to be 2 upon h square, and integration of y square will be y cube upon 3. After putting the limit, it will be coming as h cube upon 3. So this is getting cancelled, h cube. So ycm is coming as 2h upon 3. Ycm is coming as 2h upon 3. Ycm we got as 2h upon 3. It is 2h upon 3. 3 is from apex. If you see, this is 2h upon 3. It is from here, apex. This is 2h upon 3. Okay, and from here, from base, it is h by 3. From base, this is from apex. Okay, and from base it is h upon 3. So from base it is h upon 3, right? So we got center of mass of triangular lamina. Next we will observe center of mass of quadrant of a circle. Okay, center of mass of a quadrant of a circle, we will see next one, right? Now we will be seeing how to find center of mass of quarter of a part of a circle. Means this arc of the circle is forming an angle of pi by 4 at the center of the circle, right? Pi by 4. It is forming pi by 4 angle here. This entire angle is pi by 4. So first of all, the steps and the process are same. First of all, we will write here lambda. Lambda will be mass of the ring divided by this length, and this length will be r theta, as the radius is r. So r theta, r into pi by 4. So it will be 4m upon pi r. Lambda we got. Now the next process is we will take elemental mass, differential mass dm. So I'll take at an angle theta a d theta mass. This is theta, so this is d theta, right? So this length will be r d theta. So its x coordinate will be r sine theta. Okay, its x coordinate will be r sine theta, and its y coordinate will be r cos theta, because this length will be r cos theta and this length will be r sine theta, right? So this length is r cos theta, this length is r sine theta. Because of symmetry, the center of mass will be lying along the y axis. So I'll be writing ycm equals to 1 by m into integration of ydm. 1 by m into integration of ydm. What is y quadrant here? R cos theta, right? Into dm. Now what is dm here? Dm will be lambda times of that length. That length is r d theta, the small infinite Simon length. This is r d theta, and lambda is 4m upon pi r into r d theta. So r is getting cancelled out from here, and by substituting the value of dm here, what I can write here, dm value if you substitute, you will get ycm equals to 1 by m into r cos theta into dm is 4m upon pi into d theta. M is getting cancelled out. Okay, and the limit of theta is from where to where? Limit of theta is from 0 to pi by 4. Okay, 0 to pi by 4. So after substituting these values, what you'll be getting as ycm equals to, you can take r by pi as common, 4r by pi as common. Okay, 4r by pi as common. You can take 4r by pi as common, and the integration of cos theta d theta from 0 to pi by 4. So integration of cos theta is sine theta, and if you substitute these values, so it will be coming as 4r upon root 2 pi. So center of mass, of this kind of circle having which is forming an angle of pi by 4 at the center of the circle, it will be coming out to be 4r upon root 2 pi, and it will be along the y-axis because the symmetry is along the y-axis if it is kept in that format. Okay.